Hello, everybody. Welcome back to another installment of our biomedical science principles and all this fun stuff. Basically, our physics level 3 course so far. So, as always, if you can, like the video, subscribe if you haven't already, leave a comment if you have any questions, or if you just want to leave some encouragement, encourage your fellow students, encourage me to keep making through these, and let's get rolling. In this video, most of this is just going to be definitions as well as equations, kind of in general, seeing what is used in these different equations and what it is that we can find with them. All right, so we start off with talking about what's called quantified charge. This is a fundamental property. It's charges that cause interactions between everything. So a lot of our chemistry in biochem will talk about bonding and different types of bonds. The way that bonding occurs is thanks to the different forces that interact with everything, and it causes them to come together in different ways. With quantified charge, we typically talk about electrons and protons. Electrons have a negative charge, protons have a positive charge. Neutrons are the third component, and they have a net zero charge, so we don't really worry about them at all. And it's the same amount of charge, just negative versus positive. So it's 1.6 times 10 to the negative 19th coulombs. Coulombs is the unit measurement that we use for charge when we talk about quantified charge. This is the smallest unit of electrical charge, also known as elementary charge. And just like we should know this, hopefully with magnets, opposites attract. The ones with like charges are going to repel each other. So a proton doesn't love to be buddy buddy with other protons. Electrons don't want to connect with other electrons because they repel each other. Next, we talked about something called electric force. So this is the force experienced by a charged particle in an electric field. This is given by the equation F, being the electrical force, is equal to the Q, the charge of the particle, multiplied by E, the electric field strength. This is essentially going to be a plug and chug situation. If you get a question involving this specific equation, just take the values, plug them in, and you're good to go. In electric field, E, this represents the force per unit charge at a point in space. We use the units newtons per coulomb. When we talk about electrical charges and electrical forces, kind of getting into that without going too deep into that, all of our different particles, the electrons, the atoms, the molecules, all of them have some type of stuff inside of them which has a charge, and especially dealing with electrons, when you get deeper into the world of physics, the way that we understand electrons, the way that we understand matter in general, is that there's specific movements of all of these different particles which generate electric fields. The electrons spin and move in certain ways, which causes the creation of these electric fields. That's as deep as I want to go into that. I really enjoyed physics in my undergraduate, and there's a lot more to it. However, let's just stick to the surface level right here. Hopefully, that's all we really need to get through this course. Jumping into what I think starts to get a little bit more confusing, we talk about electric potential energy. This is referred to as the work So remember, work is the force plus a displacement done to move a charge, Q. So when we're talking about a charge, we're talking about some type of charged particle, be that an electron, be that a proton, within an electric field over a specific distance d. This equation, so our change in potential energy, or the amount of potential energy that we have, is equal to the force times the distance or displacement, also, which also is equal to our charge of our particle, the electrical field strength multiplied by that distance. And of course, forces are in newtons, distance should be in meters. The charge of the particle will be in coulombs, like we saw above. And then electrical field strength is represented, I believe that is the newtons over coulombs. Coulombs should be the units on that. Continuing, more definition type stuff, we sometimes use something that's called an electron volt. This is the energy gained by one single electron when it moves through a potential difference of 1 volt. It is equal to 1.6 times 10 to the negative 19 joules. It is a convenient unit for expressing small energy quantities, especially in atomic and subatomic systems. Know the unit, know that it's equal to 1.6 times 10 to the negative 19th joules, and we'll move on. Again, like I said, a lot of just straight equation type stuff in this. Electrical potential. So it's the potential energy per unit charge at a point in an electrical field. So electrical potential energy, that's referring to work. Electric potential is referring to the actual potential energy at a specific point. So here, this is measured in volts. So voltage equals our potential energy equation divided by the charge of the particle. Again, hopefully a lot of these equations are just plug and chug. Capacitance, something called this is usually also referred to as a capacitor. A capacitor is what does the process of capacitance. It stores charge. So in any of our electronic devices, inside of our electronic devices, we have some type of capacitor which is designed to have electricity run into it, and it stores electricity to allow different things to work. The way that we calculate capacitance, we use the amount of charge stored. Q is the amount of charge that can be stored. V is voltage, and C is our capacitance in a unit called farads. Apologies if I cut out a little bit now and then. I'm just coughing. I have a little bit of a sore throat going on, so just trying to stay healthy. So a larger capacitance means that we can store more charge. Next is current, represented by I. Current is measured in amperes, also known as amps. This is the flow of electric charge per unit time. So it's how much electricity is flowing at any given time. This is current is equal to voltage divided by resistance. We'll talk about resistance in the next video. Resistance is measured in ohms, which talks us about Ohm's law. This equation right here, I equals V over R, current equals voltage over resistance. This is Ohm's law. Just draw a little arrow. Maybe it shows up. There we go. That equation is referring to Ohm's law. The current through a conductor is directly proportional to the voltage across it and inversely proportional to the resistance. Ohm's law explains the relationship between voltage, current, and resistance in a circuit. Reading back through it, so I did a couple checks, and every time I look up Ohm's law, it just brings up this specific equation. No, yeah, it's correct. Voltage, current, resistance. For some reason, it rubs me the wrong way that the equation is used twice in this context, but that's fine. Ohm's law is this equation, which gives us the current. More equations, something that's called electric energy. This is the energy used or produced in an electric circuit. The energy is in joules. We have voltage, current, resistance, and time. So here we have our equation, straight just plug and chug all the way through. Then we also have electric power. Power is measured in watts, voltage in volts, current in amperes, and then again resistance. Power is equal to voltage multiplied by the current. If we look at this, voltage is I'm trying to think of the correct word. Voltage, like how large the voltage. Voltage is how much goes through all at once. So it's kind of the quantity. Current is that quantity over a period of time, like how quickly or how often are we getting that quantity through. So that determines our electrical power. These equations killed me. I tried to break them down a little bit better, just so you can actually see kind of what's going on. I don't entirely understand the total point behind this. I believe it is because membranes, plasma membranes within the cells, within all of our cells, there's inside of the cell and there's outside of the cell, and there's a difference in charge. Overall, the inside of the cell is much more negative. Outside of the cell is much more positive because of the ions and stuff that live there. So this whole equation junk type stuff is supposed to be showing that. That's its whole point. But I think it just gets a little bit confusing just because of how much there is here. So considering the plasma membrane, a thin lipid bilayer of 8 nanometers, an accumulation of charged particles on one side gives rise to an electrical force that pulls oppositely charged particles towards the other side, creating a capacitor, an electric field, and a voltage across the membrane. All of this just boils down to, hey, there's positive stuff on the outside, negative stuff on the inside. Because of that, there's a difference in charge, so you get a voltage. So we look at this all, and we, for nerve cells specifically, that is a negative 70 millivolts, which is what the example is that we're looking at here. It gives us the capacitance. The capacitance of the membrane is estimated at 2, I believe this is microfarads per centimeter squared. Voltage is 70 millivolts. So we get asked these two questions. What is the electric field? And then what is the density? So we go and we look at our electrical field question. So the electrical field is related to the voltage and the thickness of the membrane. So our electric field equals V over D. Our voltage equals 70 millivolts. We need to convert this to just plain volts instead of millivolts. So that converts to 70 times 10 to the negative third. So that's 0.070 volts. Nanometers, this is 10 to the negative ninth, so this would be 0.000000008 meters. Very, very small distance. Anyways, we plug in those values, calculate it out, we get 8.75 times 10 to the 6th volts per meter. So the electrical field across that membrane, we take volts, because this is a big number, we want it to be more manageable, so we use the units megavolts, which is kind of, I always consider, when I use metric, I always think of it in terms of computer data, because you usually go with with bytes, then we have kilobytes, megabytes, gigabytes, terabytes. That's the way that I recall the order of these things. So from volts, we go up to kilovolts and then megavolts. So that is in stages of 3. So we get 8.75 megavolts per meter. That is our measurement of our electrical field across the membrane. Does that really serve us as chiropractic students and getting all this stuff? Not really. I don't know. But it's fine. We're here for a good time, not for a long time. The next thing he asked about the density of the charges, which I was a little taken aback by. Nowhere beforehand does it talk about density anywhere, so I had to look up this equation. Our charge density is measured by this Greek symbol. I don't even remember what this symbol is specifically called. Sigma. Oh, geez, that's ironic given the current state of the world, the current lingo. Anyways, sigma is equal to C is our capacitance multiplied by our voltage. We were given those values so we can plug them in. But of course, had to make it more complicated. So a little symbol, this is our microfarads. So micro is to the negative 6th, so we have to do all of our unit conversion, converting from the micro to just the standard, and then centimeters to meters. So we do all of that. Yeah, convert it to meters, and because they want the answer in micro, I believe that's micrometers. Yeah, micrometers. Because they want the answer in micrometers, we convert it all the way to micrometers. From there, it's just plugging and chugging, where we plug in the voltage, we plug in the capacitance with the new units, and we get 1.4 times 10 to the negative 15th coulombs per micrometer squared. Again, what does this benefit us? I don't know. Just, I guess if we need to do this exact equation, we know how to do it. But okay. Okay, that's all the electrical stuff. I tried to make this a little bit more interesting in any way possible. However, this is just very, very dense physics type material. So hopefully we understand things a little bit better. If anything, we can come back and we have all of our equations now nice and neat and organized, and we have all of our units. So if we need to, we can come back and we can plug everything in and chug along and get answers. All right. Thanks everybody for watching. Have a wonderful day and good luck studying.